Hello, welcome back for lesson 4.2. We are going to expand our understanding of functions into the exponential function. So in 4.1, we looked at the inverse function, and what you really don't know necessarily is we've done inverse operations. So adding and subtracting are inverse operations of each other, multiply and divide are inverse operations of each other. But now we're going to look at inverse functions, which we did in 4.1. And the first function we're going to look at is the exponential function. And then we're going to look at its inverse function. So let's go ahead and take a look at the book. So if you open your book to 4.2, to 4.2 on page 331, we introduce the exponential function. So the exponential function, I want to define it here, is a function where you have a coefficient c out in front. C cannot be 0. It can be less than 0. It can be greater than 0, but it can't be 0. And then a is your base on your exponent. And a has to be greater than 0, but it can't equal 1. So that's going to lead us to two situations there we're going to look at in a minute. The domain of the exponential function is a set of all real numbers, always. And the range will vary depending on what c and a are. And we're going to look at those situations today as well. The number a is known as the base of the exponential function. So let's look at a couple basic, just how to find exponentials. Make sure that you have your Desmos open here. And let's look at just 4. If you want to do an exponent, we've been doing some squared, but now we're going to do 4, and I'm going to do shift and 6 to get my exponent. And I'm going to do to the 3. Which that is the same as doing 4 times 4 times 4. So your exponent is a shortcut for repeat multiplication. So let's look at number 9 in your book is 4 to the 1.6. So not quite 4 squared, which would be 16, but bigger than 4 to the 1, which is 4. Then let's look at number 13 in your book. And that is the number E. So the number E is a number that is really, really close to 2.718. We use it a lot in financial formulas, and we're going to use financial formulas at the end of this section. So number 13 is E. So if you just do the little e, it would automatically know. And then I'm going to raise it to the power of 3. So it's e cubed. That's just kind of getting us warmed up. So let's look at number 21 in the book here. Number 21 is asking us to sketch the graph of each function. Now, I want you to be able to learn what they should look like in the pieces and why. This function is y equals, they call it g of x, but we're going to type it in as y equals. And then the base needs to go in a parentheses because it's a fraction, and we're going to raise it to the x. So notice what's interesting now is before we've had x as our base and we've squared x, not knowing what x is, but now x is in the exponent. And so we're going to learn some new fancy ways in lessons 4.4 and 4.5 to solve these equations, because we have to get x down into the, what I call like the main level to be able to solve for it. So we're going to need to know that inverse function that we're going to learn in 4.3 to do that. So you can see that what's interesting here is this function is 1/4 is the base, and notice that it's getting smaller from left to right. So if this were a linear equation, we would say the slope is negative. It is declining, but it's not linear, so we don't have a slope per se, but it is decreasing. Notice that it has an asymptote at y equals 0, a horizontal asymptote. And then it just goes forever and ever and ever If you go to the negative direction, it goes up to infinity here. So this particular function, let's just make some notes for ourselves here for 21. Has a horizontal asymptote at y equals 0. And the range, because we said that the domain for exponentials are all real numbers, but the range will never get to 0. So it's going to be 0 all the way to a positive infinity. So how large can the y value go? Okay, so I'm going to take you to my, I will make sure that I put this link in Canvas for you all to look at. But I would like you to go turn to my paper here, and we're going to learn about some pieces of an exponential function and why what they look like and why they do what they do. Okay. So in your book on page 333, it goes through a couple of situations. Okay, and it goes through the situation where, let's first look at where a, it has to be greater than 0, but it can't equal 1. So we have, so that means we have two situations. One is when a is bigger than 0, but it's less than 1. Okay, so we're going to usually see this as a fraction or a decimal. Okay, this is the base of our exponent when that is a fraction decimal piece. You're going to see that the graph will go something like this. Okay, so this is going to be called exponential decay. If you've ever had an MRI or certain scans done at the hospital, they inject you with a dye, and that dye goes into your body so that the scan can see the dye as it's traveling through your body. And it goes in your body so quick and comes out of your body so quickly that they have to do the scan very, very quick. And that's because that chemical, that dye, has exponential decay really quick. The domain is always all real numbers. So the domain in this situation is always going to be all real numbers. And the range is always going to be based on your exponential function. It's going to be going from 0 up to a positive infinity. Okay, because it's going to get really, really close to 0 down here, but then it's just going to go straight up. So those are the main things there. Then the other situation that a could possibly be is if it's greater than 1. It just can't equal 1. So the other possibility is that a is greater than 1. In that case, we're going to have, and you can see all this on page 33, but it's good to write it down so you can see how it's going. This is going to be exponential growth. And hopefully when you invest your money so that you can retire one day, your money will see a lot of exponential growth. And that's what I'm hoping for mine too. Money that grows very, very rapidly. And the reason that these functions decline and grow the way they do is because we're using repeat multiplication. So when you multiply things, multiply numbers, the same number over and over and over, the number gets so big so quickly. It's not like adding the same number. That would be a linear equation. Okay. And so this exponential growth, it too has a domain of all real numbers. We can put anything in, but in this case, the range is going to also be 0 to infinity. It's just coming from the other direction. Okay. So as A approaches, I'm sorry, as X is approaching from the left, from the negative infinity here, it's getting very, very, very much bigger. But as X approaches from the left up on the decay, it's getting smaller. I is getting smaller. So let's go back and look at a few from our book here. So number 25, it's this whole section is asking us to graph. So we know that this number is approximately 2.718. That's our A on this one. And so because it's bigger than 1, we know that it's going to be exponential growth. And this 2 out here is super fun because it's the new Y-intercept. So your Y-intercept is always when X is 0, right? And so if we were to put 0 in for X here, we're going to get 2 times e to the 0. And any number raised to the 0 exponent is always 1. So that number out here, C, is always going to be our Y-intercept. So for this function, we can just take a guess of what it's going to look like. It's going to start at 0, 2, the Y-intercept, and then it's going to grow quite rapidly. And we can see that in Desmos. Oops. So let's put in number 25. So that's going to be Y equals 2e to the X. Oops, I made that a capital E, so that's why it's confused. It just needs to be a small e. There we go. Okay, I'm going to turn off my other one up here. So this is the one, and you can see that when you click on the graph, it will show you where that X-intercept is, and yep, it's indeed at 0, 2. Okay, let's look at number 29. So 29, I'm going to take you back to my paper. We're just really going to try to get good at taking a guess at what these look like. I'm not going to do them all in Desmos for time, but you most certainly can. I might go put them in for you so that they're within the link. But so this one, we're going to have this Y-intercept, which is just nice to be able to plot a point. So it's going to be at 0, 10. And our base is 2. So we know it's exponential growth. And so there is our Y-intercept at 0, 10. And we're going to grow like that. Um, 33, we have the base at 3. There is no C out front. It's just the base of 3. And so our Y-intercept is at 0, 1. And that's because 3 to the 2 times 0 is 3 to the 0, which is just 1. So that's at 0, 1. So it's 0, 1, and then it's going to increase from there. Okay, 37 is asking us to answer a few more questions, okay? It's asking us to find the Y-intercept, the domain, the range, the horizontal asymptote, and the behavior. So as X is going to the negative infinity, and then as X is going to the positive infinity, what is going on with our function? Okay. So our Y-intercept is going to be 0. And if we put here, we get a negative, put the 0 in for X, we get a negative 5, a -1 because 5 to the 0 is 1. So our y-intercept, this is different, isn't it? Our y-intercept is at 0, -1, so it's down here. Okay. So our base is 5. It's bigger than 1, so it should be exponential growth. And it is, but it's in a negative direction. And you can see some of these, if you were to look at, there is one on page 334. So I want you to see this one here for number 37. Let's go to Desmos. So I'm going to put in y equals -5 to the x. And so you can see when I change that and take that negative away, it's a definite exponential growth. I'm going to turn off our old graph here. But then as soon as I put the negative there, it reflects over the x-axis, just like when we did the reflections for other functions in the last chapter. So that's kind of cool. So it's still exponential growth, but it's just growing in the negative direction. Okay. So our domain is going to be all real numbers. And our range is the largest it's ever, well, let's go by the smallest it's ever going to get. So remember, range is your y. So because it's going to a negative infinity, that's the smallest it's going to get. And it's going to get very, very close with 0, but never arrive there. So let's go ahead and show you my paper so you can see how I'm going to write those. So there's our domain. Our range is going to be a negative infinity up to 0 because it's a reflection over the x-axis going down here. It's going through that point. Okay, and our horizontal asymptote is at y equals 0 as usual. And so as x is going to the negative, right, our function is going to, f of x is going to 0. And as x is going to the positive, our function is going to a negative infinity. Okay, so it basically, these follow your range. I'm running a new function. Okay, so for 37 is the next one I wanted to look at. 37 is asking us to do the same. Oh, I'm sorry, 41 is asking us to do the same. So again, this is a base E, so it's something financial. We talked about that. And we want to know our y-intercept. So if we put 0 in for x, we're going to get 0 times 7 times 1, which is 7. So it's at 0, 7. So up here. And our domain is all real numbers, and our range is going to be 0 up to a positive infinity, because it's going to be it's going to go something like this. And they want to know our horizontal asymptote, we're just going to call it HA, is at y equals 0. Make sure you write y equals 0. Some of you are mistakenly writing x equals 0 for the horizontal asymptote. The horizontal asymptotes are always y values. And then as x goes to a negative infinity, it's the function f of x is approaching 0. And as x goes to positive infinity, the function f of x is approaching positive infinity as well. Okay, so you might just now be going, okay, I'm starting to get a little comfortable with this. This is good. But now we're going to jazz it up a little bit. So let's look at number 45. So number 45 is going to be just slightly different on some things that we thought were always going to be the same, this domain and range, because we've got this +1, so we've got the shift up. So we're doing this whole function thing for the exponential function, and then we're going to shift everything up 1. So let's look at our y-intercept. We're going to put 0 in for x. And we get -4 times 1 plus 1. We got to add the 1. So we end up with a -3. So our intercept is at 0, -3. And that -4 out here is going to be that reflection of across the x-axis here. So our domain is not going to change. It's going to be a negative infinity to infinity, but our range is going to be from 1 because it's going to be an asymptote at 1 now because of the shift. And you can see that as well in a couple on page like 336 and such. So our range now is going to be from a -3. I'm sorry, our asymptote, her range is going to go really, really close to a -1 and go to, I got to write it the other way. It's a negative infinity up to a -1. It feels like we should do it the other way around because it's this way, but it's how low can it go, which is a negative infinity, up to how high can it go, which is not quite a -1. The horizontal asymptote is going to be at y equals a -1. And as x approaches negative infinity, the function is approaching a -1. And then as x is approaching a positive infinity, the function is approaching negative infinity. That's this here, and that's this here. Okay. Now we're going to get into some fun things like how do we use exponential functions? And we're going to dive more into those in some later sections, 4.4 and 4.5, but we're going to introduce some here in the compound interest. So compound interest we have a particular formula that we're going to use for compound interest when you're investing your money. And the formula is in your book on page 337. We're going to look first at compound interest. R is going to be our interest rate. So the percent of interest that you're going to earn per year, interest rate. And that's always going to be written in decimal form in the formula. P is our principal. And when we say principal, we're not talking about the leader of your high school. We're talking about the principal amount, the amount that you're starting with. T is going to be time, and that is usually in years. So remember, if it's 1.5 years, you're going to write 1.5. And N is the number of times per year that you are, we call it compounding. But compounding really means how many times a year are they going to give you the interest. So for on number 61, if we go there and look, it says for an initial deposit of $1,500, so P is equal to $1,500. Find the total amount, that would be A. Find the total amount in a bank account after 5 years, so time is 5, for the different situations. So N is monthly. That tells us that because it's monthly, there are 12 times in a year that they will give us interest. So after 1 month, after January or whatever, January to February, they're going to go, okay, how much interest did you earn? And they put that into your account and they add that to what the money is going to grow based on. And then the next month, they're like, okay, how much interest did you earn from the last month, and they're going to add that to your base amount. That's the cool thing about compound interest, is you're earning money from your money. You're not just earning money on the initial deposit of $1,500, you're earning money from your money and from your interest that you've earned. So let's go ahead and fill out our formula. We have $1,500 that we invested. 1 plus our rate is 0.06 over 12. And then our exponent is n times t, so 12 times 5. And I'm going to go ahead and put this in Desmos, and then you can just gonna go ahead and copy that. Actually, I would go to my Desmos link and copy that over so that you've got that correct here. So this is number 61, and I'm going to just type here compound interest so we all know. So it's going to be, I'm just going to put, whoops. So it's 1,500 parentheses 1 plus 0.06 divided by 12 parentheses. Make sure that whole thing is in parentheses, and then raise that to the exponent. Now the 12 times 5 needs to be in parentheses, or it won't put them both in the exponent. Okay. So after 5 years and all of the accruing of interest every month, we should have $2,023.28, rounding appropriately, in our account. $2,023.28. Awesome. Let's look at number 59. Oops. I need to do that there. I need to do it here. Let's look at number 59. So number 59 says we're going to look at the same scenario, but this time it's with a 3% interest. 59 is 6% interest. 6% interest compounded annually. Actually, let's not do 59. That one's boring. Let's do 60. 60 is 3% interest, so a little bit different, and it's compounding semi-annually. Compounding semi-annually. So it's probably good to write down what all of these mean. So semi-annually means twice a year. So 2 times a year. So n is going to equal 2 and for this. So let's fill in our formula here. So A equals, we still have the 1,500. Our interest rate is 0.03 this time. So not as great of an interest rate, but, and we're not compounding every month. So this is definitely not going to be as much of a growth. We have half the interest rate, and we're not compounding every month. We're only compounding 2 times a year. So 2 times 5. So let's go to Desmos and see what this comes out to be. And the cool thing is I can just copy that and paste it. And we said we're looking at numbers. This is 60. But we have to make sure that we correct our interest rate is 3, and our compounding is only twice a year. And we have to fix that in the exponent as well. So yeah, look at only $1,700.81. $1,740.81. Not quite as good of a deal. There is another type of compounding that is compounding continuously. And so to do that, we're going to have a little bit different formula that we're going to look at here. And that formula is going to entail using that natural number E that we talked about. So I'm going to go back to my paper so you can see this new formula here. So that's number 65. So that formula looks like this. We don't have as much going on because the whole compounding that was in the parentheses before is now just this number E. So we still have our principal P. And then R is still our rate in decimal form. And then T is still our time in years. It's just we're going to use this natural number E, where E is approximately 2.718. And the cool thing is when we use it in decimals, it uses as many decimal places as it can. So it's very accurate. So that's why I want to make sure you're using the natural number E, or your answers will be slightly different if you just use this rounded 2.718. So let's go ahead and fill in the formula here. We have 65 is saying, let's say we have, again, we've invested $1,500 and we're going to compound it continuously, find the total in the account after T years. So they're going to give us some different T's. So for this one, we are going to invest that $1,500 at 3.25% interest times 5.5 years. So let's go check that out in decimals. We're going to have 1,500 E. Here's a little e. We have to raise that to the exponent, and I'm going to put that in parentheses so it multiplies them together. 0.0325 times 5.5. And that comes out to be $1,793.58. So I'd like to look at one last problem so that we can see a cool problem with decay. We're going to look at problem 71 in our book there on page 343. So let's go to the book here. I just got to get there, don't I? Okay, we're getting there. It's about depreciation. And it says the depreciation rate of a Mercury Sable, which is a car that we bought when I was first married, right here it is about 30% per year. If the Sable was purchased at $18,000, so we started at $18,000 and it's losing 30% per year. I'm going to write that down. Make a table of its value over the first 5 years after purchase. Find a function which gives its value T years after purchase and sketch the graph of the function. Okay. So let's go ahead and share my paper here so we can write down some things we know. So we know that a function, they didn't tell us how they wanted us to write it. So I'm just going to T function. So I'm going to say it's M of T since it's the Mercury. So we have the exponent here. So we know that we're starting at $18,000. And so we know that's our Y-intercept. So we know that's going to be our C out here. T is going to be up here. But we have to think about what our multiplier is. And because it's decreasing, right, we're visualizing it here at this Y-intercept. And it really doesn't go negative years, but this is what it starts out. But we know that it's going to decline and eventually go to where it's going to have some asymptote, right? Get close to $0 in value. This is that 18,000. And so because it is going to be decreasing, this has to be between 0 and 1. Okay, so when we think about what goes in here, it's always the percent that we're keeping. Okay, so this is always the percent we are keeping. Well, they said we're getting rid of 30%, so that must mean, because 30 plus 70% must be what we're keeping, because it has to equal 100% of the original price. So if we're depreciating by 30%, then we're keeping 70%. So that's what goes in here, 0.7. Okay. So we're going to come up with some letters to help us with that. But for now, we're just going to kind of put that together. We're going to worry about that a little bit more in 4.3. I'm sorry, 4.4. But for now, we're going to just kind of think of it like this. So we're going to look at this as our equation, and they want to know for 5 years what this will look like. So let's just do 1 year by hand so that we can see. So if we started at $18,000 and we took 30% of that, and we knew that we lost that much money after the first year, the $18,000 subtracting 5,400. So after 1 year, we should be at 12,600. So let's put in our equation into Desmos and see if that fits what we're thinking here. And so I'm going to say Y equals 18,000 parentheses. We think it's 0.70 parentheses to the X. Okay. I have to go up here and turn off this other graph. Okay. And we want to see the table. So we're going to go up to the gear and then click on the table. And we don't care about -2 and -1, but we know after 1 year, it does match right here, 12,600. So we want to know year 3, year 4, and year 5. And so there they are. Wow. So hopefully you learned a lot about exponential functions. Catch me back for lesson 4.3.